a light emission is useful but mysterious process. If there is non-human form of the God, it has to be the light, which is the ultimate source of light giving to the universe. So we are at a state of a elevated mind, and we get the elevated state of mind through prayer and through meditation that we heard here talk this thing. But by virtue of our negative thought, we lose some of our positive energy. In the molecular term, I call it is a non-radiative emission, and these non-radiative emissions are not very useful to the system. But what we look for in the molecules, that if you can control and harvest the energy using the molecules, then you can make it a lot of useful purpose. And that's what through my knowledge of organic synthesis, I made an attempt to synthesize some of the molecules. So what is needed is the polycyclic heteroatomic molecules. So these are the annulation strategy where the alkynes can react to a existing polycyclic molecule and you extend the conjugation. There are various possibilities that are there, CHOH, CHNH, there are CH-CH annulation possibilities are possible. But what we demonstrate here, that in this annulation the stronger directing group dictates, but here we have demonstrated that a weaker directing group can dictate. So this is the first demonstration that how the weaker group directing group can demonstrate, and we can construct a heterocyclic. So if it X equal to H, then you construct this kind of heterocyclic. If X equal to O, this opens up and give a different kind of heterocyclic. But nevertheless, in the both the cases, you are extending the conjugation. So this is the example that this is catalyzed by ruthenium, and this reaction proceeds in the presence of oxidants, and you can construct varieties of the molecules. These are some of the representative examples. You can put different kind of substituents at various positions, and you can account for their electronic effect, and you can account for their yields. And all these molecules are highly fluorescent. I will come back to this a little later. So we can also introduce various kind of substituted alkynes, and so there are substituents there. And what you see in the crystal structure, that this is 3 phenyl rings, and 3 phenyl rings are not in the same plane with respect to the core conjugate. So they are behaving like a rotor kind of structure, and this rotor kinds of molecules are very, very useful in the material science context. Subsequently, what we did, that we constructed another class of polycyclic heteroaromatic molecules where it form a urea, and there is a attack of this one. So this was mechanistically important for us because it first sulfur attacks ring closing, ring opening, again ring closing. So here the nucleophilic changes from S nucleophile to C nucleophile, and we constructed useful molecules. Then we extended this one. So earlier what we demonstrated, the weaker directing group dominates over the thing. That's what we know in the family also, right? Weaker always dominates over this thing, and in the family also. So we want to see here there are few possibilities are there. There are N directing side, O directing side, and there is another N directing S directing side. So here there is a weaker group. Whether this weaker group directs here or not, here I can again see that the product is originating from the weaker group. So it is not only true in the family, but it is also true in the molecular level also. The weaker group always dominates, and weaker group dictates. Here also X-ray crystallography structure shown that these 3 phenyl rings which are hanging around are again of a rotor-like structure. In the yet another project, what we did, that there is N directing annulation reaction. Here there are 2 possibilities. This is a stronger directing annulation. There is no other directing group. So of course, in the single directing group, this annulation will take place at the N site. So what we are demonstrating in this 3 projects, all these molecules have the rotor-like structure. Okay, all these 3 phenyl groups are out of the plane. So if you can consider like a 3 rotors, and you can consider like a 2 rotors. So what is the usefulness of this kind of molecules? If you look at the material science, it's flooded with a large number of paper of late. So they are used for the bioassay, DNA visualization, protein fibrillation, and various kind of imaging techniques, and detection of ion, and various kind of explosive material, fingerprinting, and various kind of electronic applications. So we wanted to see what is the issue in this field currently. That is called the concentration cause quenching. This was first discovered in the year 1954, and now it is generally believed that a molecule quenches its own fluorescence at a higher concentration, partially because of the aggregation formation, and that is called the ACQ effect, aggregation cause quenching. So common organic dyes normally with a higher concentration, they tend to lose their fluorescence behavior. At a highly concentration, a low concentration, their fluorescence, but a higher concentration there are no more fluorescence, because this is called the aggregation cause quenching. Contrary to the aggregation cause quenching, there is called the anti-ACQ effect. What is anti-ACQ effect? Normal polyene molecules, polycyclic heteroaromatic molecules, they cause aggregation cause quenching, but other molecules which are called aggregation induced enhancement, because when they aggregate, they gives a better and better enhancement, and that's what you see here. At a low concentration, they are not fluorescent, but a high concentration, they are fluorescent, because when they are insoluble or in aggregated state or in the solid state, they are fluorescence molecule. So this is a typical example of HPS molecule, how it fluoresces. And this is they are a non-emissive when the water content was low, but as in water content increases, so they start aggregating and this molecule start fluorescing. So how we will depict this thing? Because this molecule have a rotor-like structure and the rotor cannot pack properly. So as a result, they cannot aggregate, and so this is called the aggregation induced emission, or aggregation, this is called the on kind of thing. Like what happens in this thing, basically dynamic intramolecular rotation in the iron. There is a free rotation of this phenyl ring. Okay, as a result, they lose the energy by non-emissive pathway. On the other hand, the intramolecular motion, it can be restricted by aggregation state, they can start fluorescing. And these propeller cell molecules, because of this thing, they cannot have a proper pi-pi interaction. So these are the cause of the aggregation induced emission. Like what you see the emissive, like you can have a CD, you can stack them together and they will be the non-emissive when they are in aggregation state. But when you fry it, okay, they cannot be stacked properly, right? So they will be called the emission on. Okay. So what you see in the political context, this is called the aggregation induced emission. If you look at the Gorakhpur result, you call the political aggregation induced emission, but this will lead to the political aggregation induced enhancement or political aggregation cause quenching, that will be known on the later stage. So this is left to the political scientists. So what we have done here, that we have prepared a few representative molecules of my third project alone, where this is the rotor-like structure. So we have prepared in fact at least 2 dozen of the molecules. Just I am just showing some of the representative example, and we want to study the photophysical behavior of this molecule. So theoretical investigation of this molecule reveals that these phenyl rings are not in the same plane. They have a proper dihedral angle, that we have also confirmed from the X-ray crystallographic analysis. And this HOMO and energy gap is about 3.30 electron volt. And the HOMO is residing mainly on this diphenyl ring, and the LUMO is in the extended quinozoline core, which is positively charged. Okay. So we want to see, can the color be tuned by appropriate, since it is a donor pi acceptor type of system, if you put appropriate substituents in the acceptor site. So this will basically what will cause, because you want a donor substituents in the acceptor site, that should reduce the energy gap, but a electron donating substituent in the donor site should increase the energy gap. So that's what, but this will increase the energy gap, and this should reduce the energy gap. And that's what exactly seen from our theoretical calculation, that this energy gap is lower and this has a higher energy gap. So that's what you see in the emission spectra. This was emitting a 529 nanometer, whereas this objecting a 554 nanometer. You can see this is the emission spectrography. There is a rate shifting as you put a electron withdrawing substituent in the donor part. And exactly see in there also fluorescent spectroscopy. You can see there the light green color, but they are from greenish color to the yellowish color, their transformation. So if you put similarly substituents in the HOMO part of the molecules, so if the fluoro is a overall net electron donating group, this is a minus I effect and plus R effect. Plus R effect dominates over here, and methyl group being a electron donating substituent. So what would expect that with the higher electron donating group software, this energy gap should be lower, and with respect to the non-unsubstituted one. So you can see the energy gap is reducing from 3.30 electron volt to 3.09 electron volt. And you can exactly see that their emission maximum is going from 535 nanometer, 571 nanometer in the presence of electron withdrawing group. And you can see the exactly similar color. This color intensity has not come that well, but from a greenish to the yellowish color, there is basically red shifting in these cases. So now we want to see the phenyl groups are known to be the electron donating substituents. So replacement of the phenyl group with the alkyl group, either one alkyl group or two alkyl group, is expected to cut off the supply of the electron. So whether that will homo LUMO will remain still the same, or this homo LUMO profile will change. So what we see that in spite of the having a two alkyl group, this still remain the homo part, and this positively charged extended quinozolene is still considered the LUMO part in this molecule. But in that case, you would expect there to be high energy gap, about 3.4 electron volt, that are arrived from the calculation with respect to the parent being a 3.30 electron volt. And you can see the same thing reflects exactly in the emission spectrum. So this is a very good agreement between the theoretical and experimentally observed data. Okay, you can see the color from going from the yellowish to the deep green color. So there is a blue shifting. Earlier we were seeing the red shifting, but here is the blue shifting. Then you want to see the photophysical behavior of these molecules. So they have a typical pi to pi star transition, and there is charge transfer band in these molecules. Then you have a typical emission spectra around 539 nanometer, and this has about a lifetime about 11 nanoseconds. So these molecules are expected to be highly emissive in the crystal state, solution state, as well as in the solid state, and that's what we see this thing. So we want to see whether they will exhibit the aggregation induced emission enhancement or not. So what we did, that we carried out the titration. When it is in a DMF solution, it is very, very weakly emissive. There is hardly any emissive. But as you keep on increasing the percentage of water, they become highly emissive. Okay, with 99.2%, there is almost 6.2-fold increase in the emission, and you can see the transformation from a light like a blue color to the yellowish color. Okay, there is almost 6.2-fold increase with the increase in the water fraction. And you can see also the optical, the photograph in the fluorescence photograph of a DMF water solution at a various concentration of DMF water. There is transition from the basically a bluish to the yellowish region of this thing. Okay, and for, again, if you measure the lifetime of this thing, they are more stable in the aggregated state. That's what reveals from the lifetime measurement, because this is a lifetime of 1.04 nanosecond at a 0% water, at 0% water, and at 99.2% water, this is a lifetime of about 7.8 seconds. And they do aggregate in the solution state, and aggregates in the solution state. That's what we have seen, that if we increase the water percentage about 99.2 at 80 micromolar concentration, they form a typical your kind of this kind of leafy life structure, and they are highly crystalline form, as you can see from the TEM images, and this shows the basically the crystallinity of this thing. Even at a lower concentration, they form a different kind of spherical object. They form a sphere, as you can see from the FPSCM and TEM image of this compound. They are aggregating in the solution state. So then, if this kind of rotor-like structure, as the viscosity increases, irrespective of the rotor design, speed will be slowed down. That's what we expect these molecules, that as you increase the concentration of glycerol from pure methanol to glycerol, this rotation of the free rotation, which was responsible for the emission, you can see that increase in the emission as you increase the glycerol from 30% to 60% to 90% there is emission. Similarly, as you expect, if you decrease the temperature of the reaction mixture, then the rotation speed will slow down. So we did not have a variable temperature, but we measure the room temperature and the 0 degree centigrade, there is a fluorescence enhancement of this molecule. So they are typical of AIE, they have a typical AIII properties. Okay. So what is basically happening here, the increase in the viscosity and lowering of the temperature restrict the intramolecular motion of this, and there is thereby enhancement of the aggregation and enhancement in the fluorescence intensity. So many molecules, even if they are not in the planar, they can be stacked nicely, right? But rotor molecule cannot be stacked. But however, rotor can undergo different kind of designs, right? So they can have various variable designs in a 2-dimensional or 3-dimensional object, and that's what's seen in the crystal structure. So it's found that in a crystallographic thing, this says you can say there are various kind of hydrogen bonding with respect to the counter ion. There is a molecular crystallization. So various kind of weak intramolecular forces such as CHN, CH pi, CHO, and CHF are holding the molecule. Okay, you can see that there are various kind of other weak, and this pi pi stacking interaction is not strong enough, because it has to be below 3.5 to have an effective pi pi interaction. But this is way beyond the 3. This is somewhere in the range of 4.1 to 8 point something angstrom, and there are a lot of weak interactions, the highly twisted conformations, and there's fluorescence. So these all leading to the AIEEE behavior of this molecule. So when you apply mechanical pressure, these bonds are likely to break down, and this so to expect to show a mechanochromic behavior, and that's what we demonstrated, that if you make a powder of this sample in a porcelain mortar from greenish to yellow color, there is almost about a 12 nanometer, 22 nanometer shift of this thing. The color transition from green to yellow color upon grinding in the mortar and pestle and view at a 365 nanometer. This is due to the weak crystal packing of this twisted donor pi acceptor type of conformation. So during the grinding, what is happening? This molecule try to come to the same plane. So this all these weak bondings are breaking, and they are coming to the coplanar, and thereby causing a rate shifting of this kind of molecules. So morphological transformation that we have seen, that if you see the Prisman molecule, grind it, particle size decreases. We confer by powder XRD, they have a crystalline pattern, but once you grind it, they loses the crystallinity. So thereby supporting our mechanochromic behavior. So powder XRD pattern confirms that the crystallinity is transforming into amorphous during the grinding process. Another application of this thing, this is a highly fluorescent molecule, so it can have a forensic application. So this is a typical problem with the conventional dye. They will not be highly fluoresce, but this kind of dye will highly fluoresce. So this is not our work, but we just did this thing. Little bit take in a cello tape, put your fingerprint and spray our molecules. So we have demonstrated the one of the example, just few minutes. So this you can see that you can use for the forensic application also. The last part of this thing, just 1 minute I'll take, because these are the fluorescent bioprobes. You can see they are useful in the detecting the various biological species, and there's fast response, they are sensitive, low toxicity, in situ visualization and simple operation, and they have a great penetrability. So we did a biocompatibility assay, and many of these compounds are biocompatible. I just don't want to go to details. They are well within biocompatible regions, so they can be safely used, but at high concentration they are toxic, so they block one of the cell division paths. So I'm not going to the details. So this is the HeLa cell imaging, that you put this thing, this less than 10 minutes, that means the faster penetration, you can get the good imaging, excellent imaging of this compound. So this is a fluorescent image, and you can also get the 3D pattern of the molecules. Okay, so there are some other molecules you can use for the fluorescent imaging. So I end this my talk, because this is basically multifunctional AIEgen molecules, like we have the big B, who is as a part of a multifunctional role with all its equality. So I thank my research group, many of the students in the 2015, 2017, and my present research group. I thank you for your patience.